In this video, we'll practice the algebraic technique for evaluating limits of rational functions as x approaches infinity. So first, I'm going to rewrite the limit with room for division. Next, I'm going to look in the denominator to identify the term with the highest power. And then I'm going to divide everything by x squared. Always look for this in the denominator. Next, I'm going to simplify. Please, again, pay attention to your notation. I haven't taken the limit yet, so I need to keep writing the limit notation. So I get 5 plus 6 over x all over 1 minus 4 over x squared. Now I can analyze each piece. 6 over x, as x gets huge, that term will shrink to 0. The negative 4 over x squared, as x gets huge, that term will shrink to 0. We've analyzed all the pieces with x, so we can say the only thing left over is 5 over 1, which is 5. So the process of doing this analysis is kind of where we took the limit. And so I've evaluated the limit. I no longer need to write the limit notation. If you remember from your pre-calculus courses, when the degrees are the same on the numerator and the denominator, you could pull off your leading coefficients. That is a great way to double check your work, but we will ask you to show us this algebra so you can express your reasoning. And this algebra will be helpful in later situations when we have functions that mix trig functions or exponential functions. So this is a good strategy to have in your toolkit. Okay, in this example, I have again kind of rewritten the limit with room for the division. I head to the denominator to find the term with the highest power. And we can go ahead and ignore the 3 and just take the x squared. I divide everything by the x squared, and then I can rewrite this limit with the simplification. Notice that I have not taken the limit yet, so I keep writing the limit notation. X cubed over x squared simplifies to x. 6x over x squared simplifies to 6 over x. 3x squared over x squared simplifies to 3. And we can't do anything with that last term. Now I kind of look at the pieces to see what's happening, and anything with an x in the denominator and a constant in the numerator shrinks to 0. And so the pieces I'm left with basically are this x over 3. And as x approaches infinity, the top will blow up to infinity and the bottom goes to a constant. And so we have that situation where we have infinity over a constant. The final answer is just infinity. Okay, another example, same strategy. Take a look at the denominator, find the term with the highest power. The highest power is a 3 this time, so we're going to divide everything by x cubed. And then we simplify. Again, I haven't taken the limit yet, so I keep writing the limit notation so I don't forget. X squared over x cubed simplifies to 1 over x. And again, we can divide by x squared because we're not anywhere close to 0 with our x values. X is going to be huge, nowhere close to 0. We are left with 6 over x squared. X cubed over x cubed simplifies to 1. Can't do anything with that last term. Now we analyze each piece. Any piece where there is an x in the denominator and a constant in the numerator, the bottom is growing faster than the top, and the overall result of those pieces will be 0. And our numerator is entirely 0. The denominator is just 1. So we end up with 0 over 1, which is the same thing as 0. Again, we could use the pre-calculus trick of noticing that the degree in the numerator is smaller than the degree in the denominator. And anytime you have that type of situation, you should end up with 0. Great way to check your work, but we will ask you to demonstrate the algebra in this course. Later on, we will generalize that when the numerator is growing to infinity faster than the denominator, we can draw a conclusion about what the overall limit will be. When the numerator and the denominator grow at the same rate, we know that the limit should be approaching a constant. And if the numerator is growing slower than the denominator, we can draw a conclusion that the limit should be shrinking to 0.